Let's get a full screen here. So this video is going to be about limits. I have 4 limits on the board. I got my cart. I got Rennie with me, and we'll move down the wall here in a moment. Historical fact, I don't know if a lot of people know this, but Shakespeare was quite the mathematician. And when he staged Hamlet for the first time, some famous words were actually different than we've got them today, passed on to us today. He actually said, "L'hôpital, to teach or not to teach? That is the question." Yeah, true. It's on the internet. Ask your English teachers. So what are the cons to teaching l'hôpital to a calculus class early in a semester? Well, it's one of those do this, get that answers. And a lot of students have no idea what 0/0 means, nor the picture that goes with this, and how that picture leads to a kind of an elegant solution. Okay, so that's the con. The pro is you got a right answer quickly and easily. Most students are probably in that category, but I think it's important to understand what you're using, and so I did a video on l'hôpital a couple of years ago, I think, and it's my rendition of what I think you need to see. Hope I'm right. So if you want to look at that, be my guest. But here's a classic limit that's early in a calculus course. And a lot of times it's solved using algebra. You know, you can factor x squared minus 9 and divide out the x minus 3's. And you get limit of x plus 3 as x goes to 3, which is 6. And you could have done l'hôpital, you know, taking the derivative. You would have got 2x over 1. Now you don't get 0/0, so you plug the number in and you get 6. Wonderful. What's missing? What's missing is, what do you do in calculus? You find a rate. If you're given a rate, you find amounts. If you're given an amount, you find a rate, which is a nice way of saying, a simple way of saying derivatives to integrals, integrals to derivatives. You know, we're always going back and forth. And that's really the nuts and bolts of the discipline. And I think by doing it these ways and not talking about what also is occurring here, deprive students the chance to process what they're looking at. So we're going to try to do that here. We're going to try to process it. I've got x and I got x squared, which right here, by the way, keep an eye on that. And I'm going to start with a 10, and I'm going to go to a 3. That's what it means to come at this number from above. I'm going to go from 10 to 9 to 8 to 7, so on and so forth. We'll collect our answers over here. So 10 gets us 100 squared, 3 gets us 9, and change of x is 7, and 7 into 91 goes 13 times. So from 10 to 3, we got a 13 to 1 rate of change, and that's really the slope of the secant, right? From one location to the next, 13 to 1. That's occurring here. Well, what happens if I change the 10 to a 9? Well, I don't have 100 anymore. I got 81. And that's 6 into 72. And 72 divided by 6, it's 12 to 1. Okay, so that initial foray is now a little less steep, and it's 12 to 1. You might already be able to guess what the 8 to 64 is going to get us. 8 to 64, 64 minus 9, 55. 8 to 3, 5. Oh, that's 11 to 1. So let's cut to the chase. Let's go from 7 to 49. It's going to get us 10 to 1 without looking anymore. 6 to 36. 6 to 36 is going to get us 9 to 1. 5 is going to get us 8 to 1. 4 is going to get us 7 to 1. I wonder what rate we're changing at if we get really, really close to 3. Well, let's get really, really close to 3. Let's go with 3.000001. I got to count those decimal places to get this right over here. I know 3 gets me 9. If I square that, I get 9.1234567. 1, 2, 3, 4, 5, 6, 7. and another 6 zeros and a 1. I obviously didn't do it on a calculator because there's a pattern here. Now, I don't think we have to consider how far that out. That's 10, 100,000, 10,000, 100,000, million. 100 million times smaller than that decimal place. Hope I got that right. But if we divide this by the 7, 1, 2, 3, 4, 5, 6, 7, we get something very interesting. A rate of change of 6 to 1. That's really what derivatives are about. Okay, as we trend towards a small, what I'm doing here is I'm doing y2 minus y1 over x2 minus x1. That's what I'm really doing, but over a microscopic distance, right? Which tells us that if I drew this well, at 3, I'm going up at 6 to 1. At 4, I'm going up at 7 to 1. At 5, I'm going up at 8 to 1, so on and so forth. And we can kind of see that acceleration, right? And L'Hopital, if you do L'Hopital, you don't have this discussion. And this is a very important discussion to have. Let's have the same discussion over here, but let's approach it in a different way in terms of solving. And you can pause the video and see if you can make some sense out of sine x as x approaches pi from below, which means if I'm going to go to 3, and then I'm going from 0 to 1 to 2 to 2.9999, so on and so forth. Okay, so I'm going to come at it from below. And how do we do that? Well, you got to know what a radian is, right? And there's a video out there. You can look at that video and my attempt to explain what a radian is quickly. And it would be nice if you looked at that before you consider this. But maybe in the following explanation, you can learn what a radian is, and maybe it'll make some sense. I made a little circle here a minute ago. Erased that one, then I made a big one. All right, and a radian obviously comes from the word radius. And so that is a radius to the circumference of what I'm going to start drawing as a circle. But I'm going to use this distance as a measurement around the circle. And so that's 1 radius length, which is called 1 radian. That's 2 radius lengths. That's 3 radians. And I'm getting darn close to pi, 3.14. Okay? Which means I'm really looking at that distance closely. I'm looking at that distance closely. Now, the way this is written, x minus pi means that I'm doing 3.14. X is 3. I'm gonna do a little bit of drawing of a right triangle. It's the first time I've done this explanation, so like anything else, might be a little awkward, but in class, saying it over and over, just like you do problems over and over, hopefully the explanation gets better. But it's my first time trying to explain this. So I'm looking at an x value minus pi. So I'm going to look at 3 minus 3.14. Well, keep in mind then that that's a negative distance or a negative amount. Now, the sine function. The sine function is actually at 3 because I'm going to go to 3 here. All right, I'm going to go to pi in a minute. I'm going to go from here, but I'm going to start at 3. If I start at 3, it's that height, right? Because we got a unit circle. So this height, how does it compare to that? Well, first off, it's positive. That height is positive. This arc length is negative, but they kind of look like they're 1 to 1 in terms of size, right? Very much so. And let's look at the sine function here, because what you're really looking at is the sine of x minus the sine of pi, which is exactly what we did in the last one, y2 minus y1 over x2 minus x1. But we're kind of looking at it pictorially, right? And I had to get a little gap here. You know, I blew it up here, but you can kind of hopefully see that that arc length and that altitude are pretty much the same. Now, as I move towards pi, they're going to get even closer and closer and closer. Okay, but remember, this little bit is negative. This little bit over here is going to be positive. And so I'm going to get -1. Well, let's look at the sine function. Okay, where's pi? Does it look like you might be going down at 1 to 1? I think so. If you drew a tangent here, it's quite believable to me that your rate of change could be -1. Okay, and so I'm trying to get a feel for a derivative. And L'Hopital doesn't let you do that. Now here's a limit coming at you from a numerical table. Pause the video and see if you can find it. Right? I mean, I think I'm starting to use the word differential in many more contexts now. Used to use it only with the exponential function, but I'm starting to say, look at the differentials. Okay, now maybe you don't know what that means when I'm asking it. Well, that's okay. We started a conversation, we talk about it, keep working with it, devise more problems like this, and then you put it in your pocket. It only takes, 2 minutes to have the discussion, and then you can practice these problems. And 20 seconds, you do a problem, move on to something else. All right. So look at it, pause, and I'm just going to look at it. Well, I'm looking at a differential here. And I believe that's 32 units of change. That's 32 units of change. Then I'm going to look at the next one. 39 to 23. Oh, that's 16 units to change. You may already have the pattern. Right? And math is it's a lot about patterns. 23 to 15, 8 units of change. Question is, what's the limit? What's it trending towards? It seems like a pretty popular word these days, the internet, trending. Okay, so where's this trending? Well, I think we're going to go down, how many the next time? Hope you said 4, we're at 11. Hope you said 2. Yeah, 2 from 11, 9. I don't want to lose track of where I'm at. Down 1, 8, down a half, 7.5. Well, I hope you say that the limit, let's call this f of x now, as x goes to what? Well, I think there's a pattern here, right? It looks like it's going up by 50. And if I keep going up by 50 forever, I think I'm heading towards infinity. And where's this function trending? Sure looks like it's trending to 7. What was this equation? All I need is 2 values here, right? If I've got my limit, there's 7. How do I get to 71? I guess I got to go up 64 units. Next time I don't go up 64 units. Next time I go, so this is changing by a half, right? So where am I here? 60, 30, 39. Okay, so how do I get from 7 to 39? 32. Well, there's my half. Does that look like it's half of 32? Half of 16? Half of 4? Well, that's what you're trying to process. And the x values, I could put it in terms of time. X minus 1853. That was a very good year. I have a lot of friends from that year. 50. Okay, that was this equation. Wow, that's the most important y value on the board. All right, one more problem. Zipping through this pretty quickly. Got my Rene right here. Oh, okay, come on. Slide over, get that side of the chair. All right, so now, maybe you understand what this means now. So we're looking at 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0.5, 0.25, half, a fourth, eighth, so on and so forth. And why don't we pick numbers bigger than 0 that are easy to work with? You stop the video, pause it, see what you say. I'll just start with 16. Okay, what's the exponent on top of 4 to get 16? 2. Then I'll drop to 4. What's the exponent you put on top of 4 to get 4? 1. Then I'll go to 0. Okay, we've already got a nice pattern here, right? I think 0 is going to get me 1, right? I think I'm dividing by 4 here. Okay, I think the next one's going to be 1/4. 1/4, what's the exponent you put on top of 4 to get 1/4? -1. So what's 1/16? Dividing that by 4 going to get me? -2. What's 1/32 going to get me? -3. Okay, so where's this thing going as I go? I hope you can see my x's are heading to what? Hope you see they're heading to 0. What are my y values heading towards? Pause the video and think about it. I think I can keep counting in that direction forever. I think it's negative infinity. Okay, so we've been graphing these, right? And when you graph a log, you want the parentheses, the argument of the log, regardless of the base, you want it to be 0. You want it to be 1, and you want it to be the same as the base. Because then you can graph these things easily. So when is this equal to 0? 0. There's your asymptote, x equals 0. When it's 1, what are you getting? When it's 1 for an x value, you're getting 0 for an amount. When you put in a 4, what are you getting? You're getting 1 for an amount. And we've been graphing these, and we have not yet been looking at this part of the graph, where the asymptotic behavior occurs. The x values here are not going to be changing much. Sorry, out of camera view. These aren't changing much. That's what asymptotic behavior is all about. End behavior, somewhere, not locally. I hope I'm making a correct statement there. I don't have any formal training in mathematics. Maybe that's why I come at it a little differently. But the bottom line is I can see the trend, and that's the answer to this question. And I think folks can handle starting that conversation and hopefully making some sense of it. So let's actually do one more log. Let's actually graph a log, because we're not there yet, being able to graph those easily, and I'd like to be, certainly by midterm, having a lot of people look at this and graph it in 10 seconds or less. How are we going to do it? Let the parentheses equal 0. Well, the parentheses is made up of 2x minus 6. Okay, that means I need numbers bigger than 3. Because when you put an exponent on top of a positive base, you always get a positive number, and this is the inverse of that. So I need positive numbers in here. And the closest thing to a positive that isn't a positive is 0. That's the closest thing. This is a base 4. We know that already. So I've got asymptotic behavior like that. Okay. Now, the first data point, I want the parentheses 2x minus 6 to be 1. Well, that's not too bad. That's just 7/2. So we can put that there. And then if we make it 7/2, we get 1. And that's nice, because that makes 5 times 0 plus 7. Remember, what do you put on top of a 4 to get a 1? A 0. You got to hear that a lot. That doesn't come easily. That if you're just starting to study algebra, that takes a little while. So we keep looking at it. All right, now where the heck was I? 7/2. Oh yeah, I guess I get 7. One more to do, and keep in mind that's a 1. That's the difference from 3 to, and that 1 is that differential, horizontal in this case. What do you think the next differential is going to be? I think it's going to be 4. But we want 2x minus 6 to equal 4, right? So 2x minus 6 equals 4. Okay, so 10, 5. I think we're looking at the number 5. And I just made a mistake. That's right, because of the multiplication by 2, that's why that's 4. I believe, but I'm on the fly here. So misspoke, but I'm not going to stop. I'm at the end of the video. So what do we have? I forgot where I was. Oh, 10, 5. So this is 5. I've got a real feeling that's what's causing that mistake on my part. And so now if I put 5 in, 10 minus 6 is 4. What do you put on top of a 4 to get a 4? 1 times 5 is 5, plus 7 is 12. And now I hope we have a little better feel for what's going on here, right? From what we did a minute ago. And if not, that's okay. It's planting a seed. And the next time we talk about it, it's not the first time the brain's seen it. And hopefully we can process. All right, so that was quick. And I hope I said most of the things I wanted to say. I always finish these videos and go, oh, I should have talked about that. Anyway, hope everybody's doing all right. And back in class in a couple of days. All right, bye-bye.